thing that some of you might have as a complaint is the energy-based models are outdated. I should be very sad if you say that, but that's true. But energy-based models are, I mean, the original form, they are not anymore that fancy anymore nowadays. But the point is that most of the things that are working nowadays, the most important one, the diffusion model, are actually deduced from this kind of thinking. So it's very important that we understand their fundamentals. So I'm not going into details in many senses, even though that's very sad for me. But the point here is that the things that we are discussing here, you really need to know them in order to start grasping what, for instance, we do in diffusion models. And many people would say, oh, diffusion models are very complicated because they are working with the statistical mechanics. But once you understood these stuff, then diffusion models are not that complicated. And as you're going to see here, these are as well not very complicated, even though they are all coming from statistical physics, but there is no reason for that to be complicated. So that being said, it was just a bit of motivation to keep on with me when I'm teaching. So now the point here is that if you don't want to do autoregressive modeling, then the alternative way is to just come up with one model which is representing your distribution. And hopefully that model is going to have a bunch of good properties that is going to help you get rid of the issues with sampling, for instance. Now, let's take a look at this problem now. So say that I don't want to do autoregressive. Now, I just want to directly model my distribution. So I want to write down one computational model, so one neural network, super complicated, which is going to give me the data distribution, right? And then I want to give the samples to it, use maximum likelihood to train it, right? This is possible, in theory at least, right? Now, the thing that we need to do here is that we need to come up with one idea that we can build a distribution, right? So I want to have a kind of model which is capable of computing a distribution. And you might tell me, okay, let's put a softmax at the output. But remember, we talked about this fact that when we are dealing with real data, the number of cases you have, that table of possible outputs, is exponentially large, right? So you cannot do softmax, obviously, right? So we were able to use softmax in autoregressive model because we were sampling every single dimension at once, right? But here, we cannot do it, right? I am talking about one model which is taking the sample x, and then it gives me the probability or density value, right? And this is an issue because it's going to be exponentially large with d. And the other thing is that sometimes, many times, I can think of having all those entries inside x to be continuous, right? And in that case, I mean, essentially, softmax is not going to work. I need to have some alternative, right? So the idea here is to use what we call it the Boltzmann formula, okay? And what is that Boltzmann formula? Let's start with looking at the properties we need to have a distribution. Say I want to have a distribution. So I want to make one PW. So the W here are the parameters, but right now it's not important. I want to write down one function, which I can guarantee this is a distribution. So what kind of properties that function needs to have? The first thing is that this should be non-negative, right? Probability or density cannot be negative, right? So it should be non-negative. This is right. And the second thing is that, what's the second requirement for a distribution? Adds up to 1, exactly. So it needs to add to 1. It means that if x is discrete, then you need to just go after every single outcome, sum them up. It should be 1. If it's continuous, you integrate over the whole data space. It should be 1, right? So these are the requirements that your function needs to have. So you cannot leave any distribution there, neural network there, and say this is a probability distribution, right? That neural network that you put there should satisfy these properties, right? So in this small single dimension case, softmax is satisfying these properties. It's okay, right? But if this is not the case, then what we can do? So the idea, the Boltzmann formula is interesting formula because this is going to give us this possibility to get any function and then turn it into a distribution. And how we can do that, say I have this particular function f, and this function is taking one data point, one x, right? One sample, I give it to it, and then it's going to return me one real value, one scalar, right? So that f is one neural network taking the data point, the image as input, and giving me one value at the output, right? So this is the function that I have, and if I have this function, I can build one distribution out of it, and that distribution can be built by doing these two operations. The first one is that I take this f and put it in the exponent of one exponential function, e to power minus f. That guy is always positive, right? E to power anything is always positive, right? E function is like this. It never goes below the axis, right? Doesn't matter. E to minus, plus is always above, right? It never goes below, right? So this guy is always positive. The first requirement is satisfied. The second thing that we do, we take that exponential function that we had. So this exponential function, I put it here, and I divide it by one normalization factor. That normalization factor z, I define it to be the sum of this exponential function over all possible x's. Okay? So you think of any possible x inside the data space, I add them up in this form, and this is going to be called z. Okay? If I divide the whole thing by z, then I can claim this is a distribution. And if you don't buy it, I'm going to show it in the next slide. But everybody's clear what is the Boltzmann formula? So e to power any function that you have divided by the same term added up over all possible cases. Okay? Now, I put here one thing called theta. This is the temperature because this is originally coming from statistical mechanics, and this is really temperature of the system, thermodynamic system. And this distribution that you have here, this is what we call a Boltzmann distribution in statistical mechanics. Okay? You had this temperature in your assignment 1, but I'm going to get rid of it very soon, so no worries about that. But in general, what you're going to have here, theta is going to show up in the exponent, and because theta is an exponent, when I am adding up everything, that addition is going to be also depending on the temperature, right? Meaning that I change theta, this normalization factor is going to change. Any questions? Yes?
This looks exactly the same as softmax.
Softmax, yes. Yeah. Softmax is actually one Boltzmann distribution. Essentially, anything that you have, any distribution is Boltzmann. I'm going to show you. So, questions? No question? Great. So now, this guy is a distribution. You can see it immediately. First of all, if you just take a look at that expression, because exponential is not negative, this guy is not negative. Exponential is positive. This guy is strictly positive. This denominator is also strictly positive, right? Because sum of lots of exponentials is also positive. And because of that, this expression is always positive. It's actually not non-negative. It's positive, right? Like it cannot be 0. If you want to make it 0, you either need to send that theta to 0 to just, blow up the exponent, or you need to have your function very large, right? This is the only way you can make it very close to 0, but it would never be absolutely 0, right? So this is the first thing. And the second thing is that if you add it up, so if I add this distribution, it means that I look at this expression here and do summation over all possible x's. Let's see what's going to happen. This 1 over normalization factor z, does it depend on x? Yes or no? No, right? It was essentially summation over all possible x's, right? So I got rid of x, right? So this 1 over z is coming out of the summation, right? It's going to be 1 over z times summation of this expression, right? And this expression itself is z, right? Correct? So it's going to be z by z, which is 1, right? So it doesn't matter how you put that function f. What is that function f? This expression is always going to be 1. Clear? Questions? So if you have a non-discrete variable here, so instead of x being discrete, you have a continuous one, then instead of summation, you're going to have integral. But then the same property is going to happen, right? So this is going to be integral, then 1 over z that does not depend on x coming out of integral, and then you're going to have, again, z by z. So it's true in both cases, but I am eventually always looking into the summation case because that is easier to explain. Any questions? No question? Great. If you got no question, then let's define the Boltzmann distribution once clearly. So this is what we call is Boltzmann distribution. This theta here, as I told you, is the temperature. And one interesting thing that you might like to know is that this Boltzmann distribution is actually the solution to the second law of thermodynamics. Do you know what is the second law of thermodynamics? Entropy always increases. Great, right? So this is what people for a very long time believe that they can explain anything in the nature, right? So entropy always goes up, right? And when entropy goes up, there is something we call the free energy is going down, right? It's going to be minimized, right? And then if you have one thermodynamic system, do you know what is a thermodynamic system? A glass of water. Why it is a thermodynamic system? Because it has lots of molecules in it, right? And the number of molecules that is in it is out of the range you can count, right? So it's not easy to start writing down Newton equations for every single of them to see where they are going to go, right? Eventually it's not going to work, right? And because of that, what you're going to do, you're thinking of it as a many-body system. So it has so many particles in it, 10 to the power huge number, yeah? And that thing is your x, and now you want to see how it behaves statistically, right? You want to explain it. And now you start to explain it by writing down the second law of thermodynamics. You say, I get this thermodynamic system, I isolate it from the world, and then I want the entropy to go up, right? Just go up, have more confusion, have more uncertainty. And when you solve that optimization problem, you're going to end up with this solution. This is going to be the solution to that optimization problem. And f that you see here is going to be the function which is describing the energy inside the system. Like you look at every single combination of the parameters of the molecules of the glass of the water. So you have like, I don't know how many, but lots of molecules, right? And you explain every single molecule with its velocity, for instance, right? And then you have this huge vector. Then you assume there exists one function. We call it energy function or Hamiltonian. This is going to take this huge vector and compute one scalar energy out of it. So it says if the molecules are moving with these speeds, then this is the energy. If you change the speed, then the energy is going to change, right? So this F is essentially the energy that you have, or the model for your energy that you have. And then if you think of that function to be well defined, then essentially the distribution of those particles is going to be this one. Yeah? This is why we call it Boltzmann distribution. And theta is, as I told you, literally the temperature, right? The temperature of that glass of water. Okay? So, but I mean, you do see that I'm trying so hard not to get involved, but I cannot. So, yeah, this is a very interesting thing. I mean, this domain and the connection between statistical physics and statistical learning. But I just leave it as a kind of motivation to you if you're interested to get to know more about it. So, for us here, this Boltzmann is just one function which is capable of getting any function, and the function here for us is a neural network, right? It's able to get any neural network, f, right? That neural network f, which is having a bunch of weights, this Boltzmann formula is capable of taking that model and turning it into a distribution, right? And There are a bunch of things, terminologies here. First of all, that theta that I told you, temperature, we really call it temperature in generative models as well as the one you had in your assignment 1. But we usually don't use it when we are doing the training, right? We just leave it if we want to use it for invariance. So from now on, I'm assuming that theta is 1, because the main reason is that my model has so many parameters that I don't care anymore about one single scalar, right? So I don't really need to have that theta anymore. So that's going to make the notation easier. And this function f that you see here in the Boltzmann formula, I'm going to call it energy model, essentially because it's somehow the energy of the imaginary thermodynamic system. Okay? Just borrow terminology from statistical mechanics. Now, the other guy, that z guy here, this is what we call it partition function. That normalization factor, we call it partition function. Again, the term is literally coming from statistical mechanics. So there people call it partition function. And in statistical mechanics, partition function is the only thing you need to know to explain the whole system. Anything of that system can be explained by partition function. You're going to see that here again. Dealing with this partition function is the main challenge that we're going to have, and we need to get somehow over it. Okay? So that normalization factor is what we call a partition function. One important point here is that you should pay attention to the fact that this partition function does not depend on x on the sample, but it depends on your model parameter, right? Because you are summing up this term over x, right? When you sum it up over x, x is not showing up after summation, right? But weight is there. If I change weight, the whole summation is going to change, right? And because of that, this partition function is a function of weights, is a function of your model parameters, but it is not a function of your x value, the sample value, right? Everybody's clear? Questions? No question? Great. So if you got no question, then what is an energy-based model? Essentially, if you look at this Boltzmann formula, whatever neural network you have, you can take it, and then you can convert it into one distribution, right? If you do that, so if I get one neural network, and then I use Boltzmann formula to compute the distribution out of this neural network, then I am essentially working with an energy-based model, right? So energy-based model itself is essentially a neural network, right? But that neural network, I don't look at it as a distribution. I look at it as the energy of the Boltzmann distribution, right? So whatever that neural network is going to give me is going to be the energy. I put it in the Boltzmann formula, and then I get the distribution, right? Everybody's cool? So any learning model FW, whatever you have, any neural network that you have, you can essentially turn it into a data distribution by passing it or by using this Boltzmann formula, right? And when you do that, this is what we call it an energy-based models, EBM. So EBM describes one Boltzmann distribution with the energy model that is given by your particular model. So one thing you should keep in mind from now on, don't get confused. You are always working with energy model, right? There is no distribution anymore here. Why? Because Boltzmann, once you have energy, is going to give you the distribution, right? So you leave that part to Boltzmann formula, and now you can work with energy model, right? An energy model is simple. You just need to get one sample point x, one image, and convert it into one number. And you can simply write down one very complicated neural network or very shallow neural network, which does that, right? So you have energy model in your hand, and you just use Boltzmann equation formula to just turn it into a distribution. Everybody's clear? Questions? No question? Great. Now, you might say that, is there any specific reason that we are so excited about Boltzmann? Yeah, well, he was a good guy. This is one reason. But the other thing is that the Boltzmann formula that you have is essentially very generic. So meaning that it's not a specific kind or class of distributions. It's pretty much most distributions that you can think of. almost all of them. So what do I mean by that? Well, this is a bit of informal argument I put here. I don't want to get into too much details of and technicality. But one thing that we could say, like in general, is that if you have a distribution which is well defined, right? And by well defined, I mean right now think about density function. Don't think about what is it? The mass function. Don't think about discrete random variable. Just think about density function. That's easier to think about. Then in that case, I mean that function is a kind of nice, smooth function. It's not going to touch the zero at one particular point and come up, right? Those kind of behaviors are not happening, and most of the distributions you know are of that kind, right? Most distributions you know are very smooth. They're really, densities are not literally zero at any point, right? They get very small but never zero, right? So if you have one of those nice distributions, which most of things that we do know are of that kind, then you're going to find one energy function, one function f, which is going to be an energy function. You put inside the Boltzmann equation, you're going to get back to that distribution. You don't believe me? Just think about the Gaussian distribution. This is the Gaussian distribution, right? X is one single scalar. I assume that this is distributed normally with mean 0 and variance 1, right? This is going to be the PDF of the Gaussian distribution, the density function. Everybody agrees? Cool? Yeah. Now, what I can do, I can define the energy function to be x squared half. Exactly the guy who is in the exponent, this one, x squared half. Then, what should I do next? I need to compute the partition function, right? So I'm going to put it inside the expression for partition function. Partition function is e to power minus my energy model, e to power minus x to a half, dx, right? I just integrate it over the whole real axis. If you do this integral, it's going to be a square root of 2 pi, right? Then, if you want to make a Boltzmann distribution, then it's going to be the Boltzmann distribution is going to be 1 over z, which is square root of 2 pi, times e to power minus x squared half, right? This is again the Gaussian distribution, right? Gaussian distribution is the Boltzmann distribution with energy function being x squared half, right? So this is exactly the Gaussian distribution, right? So it doesn't mean that Boltzmann is a cool kind of distribution, which is covering a bunch of cases. No, it's almost covering anything that you can think of. You only need to come up with the right energy model for that. Yeah? So one other example that I can give you to just show you that, I mean, we're going to use it a bit later, so it's nice to have it here. And if we don't want to have, I mean, if you don't want to think about a continuous random variable, not a density function, but a distribution in the sense of a mass function. So you think of a discrete random variable, and then you want to look at the probability. Again, you can think of the most of the distributions that you know, you can think of them as a Boltzmann distribution. So for instance, say I have this particular Bernoulli distribution. So Qx is p when x is 0. So x is going to be 0 with probability p, and it's going to be 1 minus p with probability 1. Okay? This is not density anymore. It's a mass function, right? So the probability of 0 is p. The probability of 1 is 1 minus p, right? And then what you can do, you can, I am first of all defining this notation here because things are going to be easier. So sigma inverse is actually the inverse of the sigmoid function. I don't mean 1 over sigmoid. I mean that if beta is sigma inverse p, then p is going to be sigma beta. Do you see this? So when I say sigma inverse p, I mean that whatever the value was given to the sigmoid function to Cp at the output, right? So I mean inverse with respect to conjugate, with respect to, argument, okay? So if I define the sigma inverse to be the inverse of sigmoid function, then I am going to define this energy function. So my energy function f is this particular constant, sigma inverse p. This is one constant. This is one value, right? Times x. This is my energy function. Now, if I put this energy function inside the expression for the partition function. So what is the partition function? Is e to power minus energy and then add it up over all possible x's. What are the possible x's here? 0 and 1, right? So essentially, I need to compute this guy at x equal by 0 and x equal by 1, right? At x equal by 0, this e to power, this exponential term is going to be 1, right? E to power 0 is 1. And at 1, it's going to be e to power minus sigma inverse, right? So it's going to be 1 plus e to power minus sigma inverse, right? Correct? Everybody's cool? So this is the partition function. Now I want to compute the Boltzmann distribution at the point x equal by 0. What I'm going to do, e to power minus energy function at 0 divided by partition function, right? So I'm going to write it down. So p at point 0, this is the Boltzmann distribution at point 0, is going to be 1 over the, because e to power minus 0 is 1, right? So 1, the value at point 0, value of the energy at point 0, divided by the partition function, right? Now, look at this expression. Forget about that green term. What kind of function is that? 1 over 1 plus e to power minus argument. What is it? One over 1 plus e to power minus x. What is it? Agreed? Is it sigmoid or not? Am I right? Yes? Okay, this is sigmoid function, right? So that 1 over this red term is essentially a sigmoid function, right? Right? So I am computing sigmoid at sigmoid inverse of p. What should be this term now? P, right? Great. Okay, cool. So it's going to be p, right? And this is exactly q at point 0, right? So when q at point 0 is same as p at point 0, then q at 1 should be same as p at 1, right? And this means that your Boltzmann distribution is exactly your Bernoulli distribution, right? Everybody's clear what I'm doing here? Yeah? Questions? Yes?
It's not related to this example,
Yeah.
but like in more general cases, when we have, let's say, our distribution is not well defined, and we kind of need to find that energy function. What's a good way of finding it? Because it can be anything, right?
The energy function.
Yeah, the energy function, because here it said the energy.
I'm coming up yet. This is why we learn the energy function, right? We keep it, leave it to be a neural network, and then we train it, right? Because we don't know what is the energy function. These are dummy examples. I can simply engineer the energy function. But in practice, we don't know, so we're going to learn it, right? We're going to train the model based on data, of course. This is the whole idea, exactly. So, any questions? No, yes?
Explain again why the numerator is 1.
Sorry, why the?
Why the numerator is 1?
Because it's e to, I mean, just think about the Boltzmann expression. It's, the Boltzmann expression is, where is it? It's px is going to be e to power minus f of x divided by the partition function, right? And then f at point 0 is going to be, if you look at that f, is going to be e to power 0, right? And this is going to be 1, right? Questions? Everybody's clear? So, moral of the story here is that this Boltzmann formula is quite general formula. And then anything that you have in nature, you can essentially think that this is distributed by one Boltzmann distribution whose energy model is unknown to you, right? And then the only thing that you need to know is to find out what is the energy model, right? So instead of learning the distribution itself, it's better that you go ahead and learn the energy function, right? So this is the main idea of the energy-based model. So you would say, OK, since Boltzmann is very general, so I'm going to rely on that one for distribution. And I'm going to only look for the right energy model that is explaining the data I'm dealing with, right? And this is what we call it computational energy-based model. So if you have any computational model, then you can essentially use Boltzmann formula to write down the corresponding distribution. So then that particular computational model is going to be a computational energy model, right? So